So the topic for today is titration, specifically strong acid with a strong base. Okay, I titled this strong titration because there's another lesson later called weak titration, that is a strong acid with a weak base or a weak acid with a strong base. Now this one today, all the acids and bases are strong. So that means it is 100% ionized. We don't have to deal with equilibrium. And we'll be calculating the pHs of various stages of this titration. And also we'll talk a little bit about indicators. So first, let's do a review of titration. You did learn this in grade 11 chemistry, but then again, I can't expect you to remember that. So what is the titration? A titration is a process designed to determine the concentration of an unknown solution, okay, using a neutralization reaction with another solution that we do know the concentration of. Right? So for instance, you have, let's say, a flask of acid. You would like to know the concentration of that acid. Well, you can easily measure its volume, okay, and then all you have to do is start adding a base to neutralize that acid. You add a base that you know the concentration of, or a standard solution, and you measure how much base do you need to add to completely neutralize that acid. And then once you get there, you can calculate the concentration of that acid. Okay, so the titrant in a titration is the solution you put in the burette. The burette is a long tube, usually a base. Usually we determine the concentration of acids, but you can do a reverse titration. You can determine the concentration of a base with an acid, same thing. That would be the titrant in the burette. Okay, you know the concentration of the titrant. You either made it yourself in the lab or you bought it from the store, so you know the concentration, and that's the whole point. If you didn't know the concentration, then it's a pointless activity. The sample refers to the compound in the flask, something that we are trying to determine the concentration of. So we don't know the concentration of that one, and the whole goal is to figure that out. And titration is set up like that in the picture. You have a long tube, the burette over a flask, and then there's a stopcock. If you turn that on, the solution in the burette will start to drip into your flask. And if you just let it flow, that's not good practice. You have to add the titrant to the burette 1 drop at a time in order to achieve something called the equivalence point. Okay, and then you will know that your reaction is over. So you slowly add the titrant. The key word is slowly, until the sample reaches the equivalence point. What is the equivalence point? Well, the equivalence point, also known as the stoichiometric point, is the point during the titration in which your acid exactly cancels out your base. Okay, all the reactants, the acid and the base, are completely consumed, with nobody left over. It's not enough to completely consume the acid with the base. No, you have to use the exact amount of base to consume all of the acid. You can't just dump an ocean of base in there and neutralize the acid, but you would have leftover base, and that's not the equivalence point. It has to be perfect. Now, since you know the concentration of the titrant, you have to determine what volume of titrant do I need. Once you reach that specified volume, you can then calculate the concentration of the sample, because you also know the volume of the sample. This is a stoichiometry calculation we learned in grade 11. So here is a typical acid-base titration equation. HA stands for the acid. BOH is the base with the hydroxide. You make a salt, AB. It should be BA. B is obviously the metal here. And then water, okay? And lowercase a, b, c, d are the numbers, the coefficients to the balanced chemical equation. Now, if HA is your sample, you're trying to determine the concentration of your acid here, HA. And BOH is the titrant. You know the concentration and the volume of that. You can calculate the concentration of the sample using this strategy. You multiply together volume and concentration of the entity that you know. You know the volume of the base and the concentration of the base. So if you multiply volume and concentration, in grade 11 we learned that that will give you moles of that substance. All right, volume times concentration of the base, you get moles of the base. How many moles of base did I just add here? And you can use the mole ratio between acid and base in the balanced equation to convert the moles of base into moles of acid. Okay, you divide by the moles of base times the moles of acid according to the balanced equation. And then now you end up with moles of acid. So you want concentration, and concentration is moles per liter. You simply divide by the volume of the acid you originally had, which you do know. You can measure that. Right? And this will give you the concentration of the acid. Okay, so that's just a little review of titration from grade 11. Now, you did learn this last year. We're going to do a little bit of review, one example question just to refresh your memories here. So what volume of 3 molar hydroiodic acid, HI, must be added to a 15 milliliter sample of 2.5 molar potassium hydroxide solution in order to reach the equivalence point? So you're trying to reach the equivalence point, trying to neutralize that 3 molar hydroiodic acid. Yeah. What volume of acid do you need to add in order to completely react with the base? You see what I mean? You know the volume of the base, potassium hydroxide, which is 15 mils. You know the concentration of the base, which is 2.5 molar. You know the concentration of the acid. All you have left is the volume of the acid. You know 3 things. You have 1 unknown. All right, so 4 numbers, you know 3 of them. Find the last one. And like I said before, you need to multiply together 2 of the things that you know. In this case, the potassium hydroxide, the KOH, you know both the volume and the concentration. So you will obviously multiply those together. All right, so first you write the balanced equation. It's a 1-to-1 ratio. So I did this all in one step for convenience. You have 15 milliliters of KOH. That's your volume. I multiplied this to the concentration of KOH, which is 2.5 moles per liter. Instead of writing per liter, I wrote 1,000 milliliters as the denominator because 1 liter is 1,000 milliliters. The reason I converted this to milliliter is so that the units will cancel out. I have 15 milliliters of KOH. I will cancel with the 1,000 milliliters of KOH. Okay, so instead of moles per liter, it's moles per milliliter, but you have to multiply by 1,000 on the denominator. So now the milliliters cancel. You will end up with moles of KOH. And because for every 1 mole of KOH, you will neutralize 1 mole of HI, you multiply by 1 mole over 1 mole. So the KOH will cancel with the KOH. I know this doesn't change the number, but you do have to write this step to convert the units into the proper units. So now I have the moles of the acid. Cool. But I want to know the volume of the acid. And I'm given the concentration of the acid is 3 moles per liter. So I just have to divide. If I take 3 moles per liter and I flip it, it becomes liter per mole, then I can cancel the moles. What I would end up with is milliliters. Okay, I prefer milliliters because the units are quite small. I don't need a liter, so that's why I changed the liters to milliliters. You don't need to do that unless the question specifies you want milliliters, but that's just my preference. So now, after you multiply all of this together, you'd have, finally, the volume of acid required, which is 12.5 milliliters. Okay, 3 sig figs. Is this clear? The trick is to multiply together two of the things that you know, volume and concentration, and then solve for the thing that you don't know using the mole ratio. All right, grade 11 chem, a little quick recap. All right, so here's the question though. How do you know that the titration is over? Right, I say that you have to add the titrant to the sample until you reach the equivalence point, and that is the magical point where all of the acid have reacted with all of your base with nothing left behind. So how do you know you're there? Because acids and bases, they're colorless solutions. They look like water. You're just mixing them together. You're not going to see a difference. So how can we possibly know whether the reaction is complete? Well, we have to use something called an indicator to signal the endpoint of the titration. Okay, once you reach the endpoint, you stop. So what is an indicator? Well, indicators are weak acid-base conjugate pairs. You should know what that means by now. An acid, a weak acid, in equilibrium with its conjugate base. And now the acid and the base conjugate pair, they have two distinct colors. That's very important. The color of the indicator will suddenly change when you reach a certain pH. Let's say 5. If you reach the pH of 5, the indicator will change from one color to the other. It won't change color at any other pH except that one. Okay, and then this will signal the endpoint. If you see a color change in your solution, then you know that you've reached that point that you should stop. Okay, so what is the endpoint? The endpoint in a titration is the point at which the indicator changes color. Notice that this has a different definition from the equivalence point or the stoichiometric point. It's not the same thing. Right? The stoichiometric point is when your reaction is complete. All right? You have the same amount of acid compared to base. Your hydronium is exactly equal to the hydroxide. They all cancel out. That is your equivalence point. The endpoint is something entirely different. It is the pH at which the indicator changes color. All right, so if you want your endpoint to signal the equivalence point, well, they better be very close. All right, if the endpoint has a pH color change similar to the pH of the equivalence point, then you can use that as the indicator. Does that make sense? So you have to carefully choose your indicator such that it will change color at the pH of the equivalence point. If you pick something that has a different endpoint than the equivalence point pH, it's not going to work. So here is a visual of what I'm talking about. This is a simulated titration. So I have here a flask. This sample contains hydrochloric acid. The green circle represents the chloride. The red with the 3 white ones represent hydronium. So this is hydrochloric acid. We are going to use phenolphthalein as the indicator. This is the most common indicator that we use. Phenolphthalein will change from a colorless solution to a pink or magenta fuchsia, whatever color you want to call this, a dark pink or purple color, once it reaches a certain pH, specifically a pH of 9. If you're in a basic solution, phenolphthalein will be pink. If you're in an acidic or neutral solution, phenolphthalein is colorless. You won't even notice. Okay? All right, so what we have to do is slowly add sodium hydroxide. If you just add 1 drop of sodium hydroxide, you're not going to neutralize all of the acid. You will be quickly consumed by the acid. You neutralize a small part of it. That becomes water, cool, but you still have an acidic solution, right? So you need to continue. Let's add another one. So if you add another sodium hydroxide, you neutralize a little bit more of that acid. You still have acid. Okay, we're not finished. There's no color change, so let's keep going. You got a third one. Oh, we're almost there. We have just a little bit of acid left. But still, that's still an acidic solution. All the base you've added so far have been completely neutralized. And you add one more. There we go. You have perfectly neutralized all of the acid in the solution, and you've used up all of the base that you've added. There's nothing in excess. Okay, so at this stage, the phenolphthalein will begin to change color. It is kind of going from colorless to a pink. So right now it's a light pink. And if you see a permanent color, if you shake the flask and the color doesn't go away, then you know you reached the equivalence point. Congratulations. This is perfect. Your acid completely reacted the base. Good job. All right, you're done. You can now write down all the numbers. You record the volume of base that you've added and use that information along with the concentration of the base and the volume of the acid. You can now calculate the concentration of your acid. If you accidentally add too much, right, you will cause the solution to turn more pink, right, due to having more hydroxide in the solution now. So now you have a basic solution. You've neutralized all of the acid, but you still add base. Well, guess what? Now it's a strong base. So you're screwing up here. Like, you can't go back if you screw up a titration. There's no way to fish it back out. It's pretty much ruined. All right, and if you continue from there, you're going to make it very basic. The color is going to turn very pink. Pretty much you failed at this titration. You now have to dump it out, wash the flask, and do it again. The information that you get from this is not useful at all. So please do not go overboard when you perform a titration. That's why we say you have to add it one drop at a time. You can't just turn on the faucet and let it drip, all right, because you will quickly go over the equivalence point. The equivalence point is a very specific point. It's like a balance on a seesaw. Very delicate. You will go over that if you just let it drip. So one drop at a time. It only takes one drop to bring a solution to the equivalence point and stay there. All right, so don't just let it flow. You have to be patient, one drop at a time. I was going to do a titration lab, at school, but, we're not doing that anymore. All right, so that was a review of grade 11 titration. All right, so any questions so far?
Wait, why can't you just add more acid to, counter the excess base?
Right, so, well, see, then you will change the volume of the acid. Right? You can't change your original numbers. You're better off just dump it out and try this again. Which is why we do multiple trials, because, people screw up sometimes. Sometimes you add too much. Sometimes you didn't add enough. Well, usually it's because you added too much, because if you didn't add enough, you just add more, right? So you do multiple trials and you take the average. Does that make sense?
Yeah.
Okay, so in grade 12, our job is to calculate the pH of the sample at different stages of the titration. In grade 11, the calculation was usually what is the concentration of the sample? Or what volume do I need to add to reach the equivalence point? Usually those are the questions, right? But in grade 12, we don't do that anymore. We calculate pH. So we have to calculate pH at 4 different stages. First, you calculate the pH before the titration. That means you didn't add anything. I just have the sample. That's a very simple calculation. It depends on whether it's acid or base. Negative log, that should get you the answer. Second, you have to calculate the pH before you reach the equivalence point. So you've added some base, but you didn't add enough to get to the equivalence point. So what is the pH now? And third, you need to calculate the pH at the equivalence point. And finally, you added too much. What is the pH beyond the equivalence point? Some of these calculations are fairly easy. Some of these are very annoying and hard. And we're going to learn all 4 calculations, which is what example 2 is about. So in example 2, you have a titration. you have 20 milliliters of 0.3 molar HCl. Okay, that's your sample. That is titrated with a standardized 0.3 molar sodium hydroxide. What is the amount of unreacted HCl and the pH of the solution after the following volumes of sodium hydroxide have been added? So you have 4 questions really. A, 0. You didn't add any sodium hydroxide. What is the pH? Okay. 10 milliliters. You didn't add, well, you didn't reach the equivalence point. You only added 10. What is the pH? And third, C, you added 20, which was enough to reach the equivalence point. So at the equivalence point with 20 milliliters of sodium hydroxide, what is the pH? And finally, whoops, I added too much. I added 35 milliliters beyond the equivalence point. What is the pH? Right, to do that, you have to obviously set up the neutralization reaction, the acid plus the base. You get the ionic compound, salt plus water. You have to balance the equation. In this case, it's already balanced with the 1:1 ratio. And you are given all of the numbers. You know the concentration and volume of the acid and the base. It's just that for the volume of the base, you have 4 different values, so 4 different calculations. So let's jump in. A, before you add anything, you add 0 milliliters of base. What is the pH? So in other words, what is the pH of the sample solution? Okay, don't even think about the base because you're not adding any. All right, so we have HCl. And HCl at 0.3 molar is a strong acid. So a strong acid would have equal numbers of hydronium compared to acid particles because it's 100% ionized, 100% reaction. So it should be the same number. pH is therefore negative log of 0.3. You just put this in your calculator, 0.523. Okay, 3 decimals for the pH because your concentration has 3 sig figs. And that's it. The pH before you add anything is 0.523, which is very low. All right, the pH is very acidic here, which makes sense. It's HCl. Does that make sense, guys?
Why do you have 3 decimal points for that one?
Right, the pH has 3 decimal places for 3 sig figs because the concentration has 3 sig figs. The concentration is 0.300, so all of those zeros at the back are significant.
Oh, I see. Thank you.
All right, so yeah, please don't screw up the specifics on the pH, okay? Okay, so that's the easy one. Just negative log, we're done. We learned that already. Here is where things get very complicated. All right, you add 10 milliliters. You didn't quite reach the equivalence point. You just added a little bit. Okay, what's the new pH? Well, you have to consider this. In your sample, you have HCl and NaOH. HCl produces hydronium. NaOH produces hydroxide, and they will cancel each other. They will react and neutralize, and they will become water. So they will reduce the amount of the other entity by reacting, okay? Eventually, somebody's going to win because they don't have equal numbers. Someone's going to be in excess, and that's the only thing left behind. Whoever remains in excess, be it hydronium or hydroxide, that will determine the pH of the solution. Does that make sense? You will take the negative log of the concentration of whoever that is left behind. So that means you got to calculate, well, how much do I have for each? So for the acid, you need to calculate the moles of the acid, and for the base, you calculate the moles of the base, and you subtract them. Okay, does that make sense? You understand the logic here? You got to subtract one from the other and see what the remaining number is. And of course, you have all the information to do that. You have the volume and concentration of both acid and base. So let's do it. You need to determine the moles of base that you added. In chemistry, we count in moles. So here is the dissociation equation for sodium hydroxide. Because this is a strong base, the concentration of the base will be equal to the concentration of hydroxide. It's a 1-to-1 ratio. All right, so you can take the volume of the base, multiply it by the concentration of the base, and then that last number, 1 over 1, is to convert from sodium hydroxide to hydroxide. So I have 10 milliliters of base. I cancel with the 1,000 milliliter in the denominator in the concentration. Now I have moles of sodium hydroxide. I need hydroxide, not sodium hydroxide. It's a 1-to-1 ratio, so the numbers should be the same. You get this, 3 times 10 to the negative 3 moles. Okay, that is the amount of hydroxide ions I have in the solution. It came from sodium hydroxide I added. You do the same thing for the hydronium produced by the HCl. HCl produces hydronium in this reaction. Again, it's a one-way reaction, no equilibrium. It's a 1-to-1 ratio. So volume is 20 milliliters. Concentration of that acid is 0.3. So that cancels, right? You have moles of HCl. I don't need that. I need moles of H3O. It's a 1-to-1 mole ratio, so you just multiply by 1 mole over 1 mole. The units should cancel. You would have mole of hydronium left. You put this in the calculator, you get 6 times 10 to the negative 3. Who's bigger? Obviously the 6, right? 6 is bigger than 3. You have more hydronium than hydroxide, which makes total sense. You didn't reach the equivalence point. Okay, that means you didn't add enough base together. Of course, there's going to be more acid. So now, next step, you subtract them. The hydronium and the hydroxide, they will react with each other to cancel each other out. So they're slaughtering each other. So who's left? Well, you do the subtraction here. You take the acid, you minus the base. You always take the small number, you subtract from the big number. So 6 minus 3 is 3. So you have 3 times 10 to the negative 3 moles of acid remaining. Did you guys follow so far? So you've determined the amount of H3O, the acid, in excess after you added the base and everything canceled. That is what will determine the pH of that final solution. So now you take negative log of this number and you will get the pH. Does that make sense, guys? No, it does not. No. You don't take the negative log of this number. You take the negative log of the concentration of the acid. This is not the concentration of the acid. This is the mole, the amount of acid. You need to calculate the concentration of the acid. Concentration is moles per liter, right? You calculated how many moles of acid I have. Cool, it's 3 times 10 to the negative 3. What is the total volume? Well, 20 comes from the acid, 10 comes from the base you just added, so they add up to 30. So you have to take the moles divided by total volume, convert to moles per liter, of course. That is the concentration of the acid, which is 0.100 moles per liter. Okay, many people forget this step. Very common mistake. You did all the addition and subtraction correct. You found the excess amount. You took the negative log. You got the wrong pH. It has to be concentration, not moles. So now, negative log of this is the pH. Okay, you don't even need a calculator for this. This is 1. So pH is 1.000. 3 decimals for the pH because of 3 sig figs in your reactant. Does that make sense, guys? Then you're finished. The pH after you add 10 milliliters is 1. So questions? All right, so let me just bring to your attention how weird this is. When you didn't add any base, you just have pure hydrochloric acid, okay? The pH was 0.5, give or take. Now you've added 10 milliliters of base, the pH should go up, and it did, which makes sense. But think about it, 10 milliliters is halfway at the reaction. You're half halfway to the equivalence point. You need 20 to reach the equivalence point. You have 10. That's 50%. And at the equivalence point, the pH should be 7. You should neutralize at the equivalence point, right? So from 0.5 to 7, the halfway point is definitely not 1. You've only raised the pH by 0.5. You went from a 0.5 to 1. Congratulations. Right, so that means the 10 milliliters that you're about to add to raise it to the equivalence point, raise the pH from 1 all the way to 7. Does that make sense? So pH increases very slowly near the beginning, and it increases exponentially faster as you approach neutrality. As to why this happens will be made clear a little bit later. Okay, so just keep that in mind. It's not a linear relationship here. All right, so C, at the equivalence point, you can basically just close your eyes and write down 7. That's it, done, moving on. Okay, I'm going to explain why it's 7. At the equivalence point, by definition, the concentration of the H3O should exactly equal to the hydroxide. Okay, if this is not true, you're not at the equivalence point. So at the equivalence point, all the hydronium from the acid is neutralized by the hydroxide from the base. They cancel. You have zero excess of neither. Okay, so how do you calculate a pH if you don't have any H3O, right? Because pH is negative log of H3O. We do, in fact, still have H3O and OH. It comes from an insignificant source that we've been ignoring until now. What is that source? Water. Remember we learned this, the auto-ionization of water. Water gets bored and starts to react with itself at an equilibrium. You produce very low amounts of H3O and OH at equal concentration. So it's still neutral, but you still have them. And empirically, at 25 degrees, we determine the concentration of H3O. It's 1 times 10 to the negative 7. That is the determinator of pH. Negative log of this number is 7. So the pH at the equivalence point of a strong acid and strong base titration is always 7. Okay, does that make sense, everyone?
Do we need to prove this every time, or you can just write 7?
Okay, see, no, you don't have to prove this. On the test, I'm going to just look for the answers, right? Normally, yeah, on a test, you would have to do this calculation if I ask it. But now, since your test is online, you can't show your work. Just write 7 in the correct number of sig figs, and you're fine.
Okay, thank you.
You're welcome. All right, so notice what I said. pH is 7 at the equivalence point for a strong acid and strong base titration. The key word is strong. If you don't have strong acid, strong base, let's say you have a weak acid and a strong base, the equivalence point is not 7. All right, on Monday, we're going to learn those. You're going to quickly realize at the equivalence point, it is not 7. Only for strong acid and strong base is a 7. All right, and also, the auto-ionization of water happens all the time, not just at the equivalence point. This was happening in the previous steps before the base was added, or you added just a little bit of base before the equivalence point. You still have this. We never bothered to calculate this because the concentration of H3O that results from this is way too low. It is insignificant if you actually have an acid. You see what I mean? It's like Bill Gates has really high income. Okay, he makes more money in his sleep than I will in my entire lifetime. And then he goes and gets a job at McDonald's. He gets paid like, what, $12 an hour at McDonald's. Do you think Bill Gates would care about the money? If he were to work at McDonald's, it's probably for another reason, not for the money, because that's something he doesn't need. he still gets an income. It's just it's so insignificant compared to his other sources of income. We don't even think about that. You see what I mean? So for the previous question, when we actually did have HCl, it is producing hydronium at high concentration, way higher than 10 to the negative 7. So yeah, water, you're helping, but realistically, when you calculate the pH, even if you add this, it's not going to make a difference. So we ignored that. But now at the equivalence point, it's different. All the acids have reacted. They're gone. It's like Bill Gates goes bankrupt. Okay, he gets removed from Microsoft for some reason. He lost all of his money in his bank account. He has no money left in his pocket. All of a sudden, that McDonald's job is looking good. That $12 an hour could save his life. Okay, he has to eat. So then that becomes important. He will probably go there for the money because he lost all other income. So that's the situation here. You've lost all the other hydronium income. The only thing you have left is water. So yeah, we're going to use that to calculate pH. You see what I mean? Just know that this is always there, but only becomes significant when everything else dies. You good? All right, so let's move on. You add way too much base and you've exceeded the equivalence point. How do you calculate the pH of that? It's the same idea. You calculate the amount of moles of sodium hydroxide you have left over, convert to moles per liter, and solve for pH. Okay, now you would have more sodium hydroxide than hydrochloric acid because you added too much. So if you subtract them, you should have excess base this time. So it's the same calculation, essentially. Calculate the moles of sodium hydroxide. Well, you added 35 milliliters. The concentration didn't change, so the 35 mils cancels with the mils with the concentration. And then, of course, it's a 1-to-1 ratio. They cancel. And you should have 1.05 times 10 to the negative 2 moles. That's the amount of sodium hydroxide or hydroxide you've added to the sample, okay? What is the mole of H3O? Well, that should be the exact same number we calculated in B because we didn't add acid. It's still there. So it's the same calculation. It's 6 times 10 to the negative 3. Does that make sense? So now, obviously, you can see that you have more base than acid. 10 to the negative 2 is bigger than 10 to the negative 3. You need to subtract the acid from the base. All right. When they neutralize to become water, all of the acid will be gone and there will be base left behind. So you do the math, 1.05 times 10 to the negative 2 minus 6 times 10 to the negative 3. Put this in your calculator. You should get 4.50 times 10 to the negative 3 mole of hydroxide. That is the amount of hydroxide you have in excess. And then you need to calculate the pH. So negative log of this, you get POH. You subtract from 14, you get the pH. Does that make sense? No, it doesn't. You cannot take the log of this. You have to take concentration. This is not concentration, this is moles. You need to divide by total volume to get the moles per liter, the concentration of hydroxide. You can't use a log of moles. So determine the concentration, moles per liter, 4.5 times 10 to the negative 3. Well, that's the amount of moles you have left. Divided by total volume, 20 comes from the acid, 35 comes from the base. That's 55 in total. You have 0.0818 moles per liter. And then you do negative log. Negative log of this number is the POH. You subtract that from 14. We've seen this many times. The final resultant pH is 12.913. 3 decimal places are needed because you have 3 sig figs in your concentration. This is quite a high pH because you have an excess of base. You're now a strong base. That makes total sense. You good? So we've learned 4 different calculations for one single question. That can get a little confusing. There is another way to calculate the pH beyond the equivalence point. That was one way. You don't have to use that method. This one is equally good, if not better. You could instead determine the excess volume of sodium hydroxide. Right? You only need 20. You've added 35. So you added 15 milliliters excess. You see what I mean? You only need 20 to raise to the equivalence point, but you went over by 15. So that's all I need. I added too much. Oops, I added 15. Okay. How many moles of hydroxide exist in this extra 15 milliliters? So you can just take the 15 times the concentration. You will get this number. There, you skip all of that subtraction from the acid. You basically did excess base. You have in excess 4.5 times 10 to the negative 3 moles of base. And then, of course, divide by total volume, negative log, you have the pH. Right? You could do it this way if you like, or you can do it the other way, calculate the moles of acid, moles of base, subtract, and divide by total volume, whatever floats your boat, okay, whatever fancies you're liking. Go ahead and pick that one. I don't care. Just give me the right answer. Okay, here is something called a titration curve. It is basically a graph. It is on the x-axis volume of base added versus the y-axis pH. Okay, it is pH as a function of volume added. You can see that initially, when you added 0 base, the pH is very low. The graph starts very low. And then it slowly rises until you're near the equivalence point. You take a rocket ship, you go all the way up, and then slowly rise again. Okay, and at the equivalence point, you have a pH of 7. The shape of this graph looks like this for a reason. Because this is a logarithmic scale. It's not linear. When you have low pH, okay, that means you have a lot of hydronium. H3O is off the charts. If you're going to neutralize that, you're going to need a lot of base. Adding a little bit of base will barely make a dent in the pH. Remember, to go from pH of 1 to 2, you need a 10-fold decrease in the amount of hydronium. Does that make sense? Let's say you had 1,000,000 hydronium molecules. To go to the next pH, like to go from 1 to 2, you need to drop that to 10%, which is 100,000. From 1,000,000 to 100,000, you lose 900,000. That's a lot to be lost. So in order to lose that, you need to add a lot of base to neutralize it. So that's why it's really hard to change the pH from 1 to 2. You need to add a lot of base to get there. And this gets exponentially easier as you rise in pH. If you have $10 and you would like to shrink to 10% of that, that's $1. All you have to do is spend $9, which is very easy to do. You can walk into a convenience store, come out, you spend $9. If I had $1 million, I walk into a convenience store, I come out, I'm not going to come out with just 100,000. I'm not dropping 900 grand on a convenience store unless I buy the convenience store. You see what I mean? So it's really hard to go from a pH of 1 to 2. You have a huge change in concentration to get there. But to go from a pH of 5 to 6 is very easy, because there's not much difference between 10 and 1 compared to 1,000,000 and 100,000. Does that make sense? So that's why you have this shape. It seems like you take a rocket ship. When you reach a pH of 3, things get really small. So boom, you go all the way up. And same story is true when you get really high in pH. To rise from 10 to 11, you need to basically multiply the amount of hydroxide by 10. Right? And let's say you have 100. Well, now we need 1,000. You need to add 900, which is a lot. But from 11 to 12, you need to go from 1,000 to 10,000. That is 9,000 compared to 900. That is way more. So that's why it kind of levels off near extreme pHs, but near the middle, near neutrality, it takes an elevator up. That's why you have this shape. And near the extremes, when the curve is flat, we call it the buffer zone. Okay, a buffer refers to a resistance in the change of pH. You really resist a change in pH near the beginning until you reach near neutrality, then boom, you basically flip from acid to base instantly, and then you have the buffer zone again. You need to know how to interpret this graph. You need to know how to draw this graph if I ever ask you to draw, given certain numbers. Okay, so you need to know the shape. If you recall calculus class, you've seen one of this before. It's when you have a pH of 7. If you draw a tangent at that point, it is the vertical tangent. That is when the derivative does not exist because the slope of the tangent is a vertical line, which doesn't have a slope. It's same as that one. It's kind of like an S shape. Not really, but you get the idea. Draw this like this. If I ever ask you, or in your future studies, somebody asks you to draw a titration curve. All right, so example 3 is very similar to example 2. I'll give you around 15 minutes on this because there are 4 questions in here. Practice, please, and I'll take it up in 15 minutes. Okay, so good luck, folks. All right, so example 3, you have a sample of 15 milliliters of 0.2 molar nitric acid, which is a strong acid. It is titrated with 0.1 molar sodium hydroxide. So determine the pH at the following stages of the titration with the specified volume. So you have 0, 50, that is before the equivalence point, 100 at the equivalence point, and 150 after. The balanced equation is there. It's a 1-to-1 ratio, and all of these values are given. So, before the titration is simply the pH of a strong acid. It is the same as HNO3. It's a 1-to-1 ratio. 1 mole of HNO3 can donate 1 proton to make 1 H3O. So negative log of whatever HNO3 is, which is 0.2, you get 0.699. Okay, 3 sig figs for, 3 decimals in the pH for 3 sig figs. That's quite simple. It's just a negative log concentration. For B, you need to calculate the pH when you add 50 milliliters of base. So that is not quite the equivalence point. They will cancel until some acid is left over. Okay, we know for a fact that we have more acid than base because we didn't reach the equivalence point. The sodium hydroxide added, well, that is 50 milliliters, that's the volume, multiplied by the concentration, which is 0.1 moles per 1,000 milliliter. It's a 1-to-1 ratio, so you should have 5 times 10 to the negative 3 moles. And of course, the moles of acid in HNO3, you have 15 milliliters of that. The concentration is 0.2 mole per 1,000 milliliter, and it's a 1-to-1 ratio, so you have 1 times 10 to the negative 2. Basically twice of the hydroxide. And the acid remaining would be the difference between the two, acid minus the base. So you have 1 times 10 to the negative 2 minus 5 times 10 to the negative 3. You take the difference, that will be 5 times 10 to the negative 3 moles of acid remaining. And then, of course, you then take the negative log, and then you get the answer, right? No. Okay, this is the 3rd time I'm reminding you that you need to calculate concentration. Don't take the negative log of the mole. Okay, it's a very common mistake. Mole of acid divided by total volume was 50 plus 50 because you had 50 acid and 50 base. That's 100, and you have to times 1,000 because you gotta convert to per liter. And you would have 0.0500 moles per liter, 3 sig fig. Finally, the pH, negative log of hydronium, it is 1.301. All right, so do we all get the same answer? It has to be exactly the same as mine, otherwise you either made a rounding error or a calculation error or something wrong. Okay, C, pH at the equivalence point is 7, done. Okay, that one is no-brainer, of course, it's 7. D, the pH after the equivalence point, you've added too much. Well, how much did you add? I added 150 milliliters. Okay. Well, how much do you need to reach the equivalence point? Well, I don't know. Well, the question does tell you. The question tells you that you need, I think, 100 milliliters to reach the equivalence point. But let's say the question doesn't tell you that. You can calculate the volume that you need to reach the equivalence point. Okay, all you have to do is perform a titration calculation like the first example that we studied. This is grade 11 chem. What volume of base do you need to reach the equivalence point? Well, 50 mils of acid times 0.2 molar acid. You multiply them together to get moles. It's a 1-to-1 ratio. And then you divide by the concentration to get the volume. Yes, of course, it's 100 milliliters. Okay, the question already gives us this information. I'm calculating just to show you that this can be done, even if the question doesn't give you. So you only need 100, but you've added 150. In other words, you've added 50 too many. So 50 milliliters is in excess. And you need to convert this to moles. You have 50 milliliters at 0.1 moles per liter. How many moles of that? Well, that is 5 times 10 to the negative 3 moles of hydroxide. That is in excess. Everything else canceled. You're the only thing left in solution. So negative log of this, no. Divide by volume to get concentration is 50 plus 150, that is 200. You get 0.025 moles per liter. That is the concentration of the hydroxide in excess after you added too much. Then is negative log. Okay, you get the POH, subtract from 14. Finally, the pH of your solution should be 12.4, okay, which is a high number. That makes sense because you have added too much base. You should have the exact same numbers as me. If not, then figure out what you did wrong. Any questions? Okay, cool. So the last little bit about this lesson is acid-base indicators. Okay, an indicator is something that changes color, and then this color change is used to signal the equivalence point. Now, an acid-based indicator is basically a weak acid in equilibrium with its conjugate base. What makes them special is that the acid and the base form have different colors. Okay, if you have the hydrogen, you're the acid, you're red. I'm talking about litmus. If you lose the hydrogen, it becomes the conjugate base. Well, now you're blue. In this equation, the IN stands for indicator. Okay, that represents the rest of that molecule. This is a huge molecule. The H in the beginning is the acid, is the hydrogen that you can lose. So you can see that it is a conjugate acid-base pair. All right. If you change the pH of the solution, that means you increase H3O or decrease H3O, H3O being a product, you will shift the equilibrium because of Le Chatelier's principle. If you shift the equilibrium to favor the left side, you will produce more red acid, which makes the solution look red. And if you shift the equilibrium to the right side to favor the product, you will make more blue base, which makes the solution look more blue. That's why indicators change color, because of the Chatelier's principle. So in acidic solution, you have high concentrations of H3O. You increase the amount of H3O. Le Chatelier will want to decrease that by shifting equilibrium to the left. You favor the acid, you're red, because the acid molecule is a red molecule. If you reduce H3O in a basic solution, because the excess hydroxide will decrease the hydronium, then Le Chatelier will want to increase hydroxide by shifting the equilibrium to the right to favor the product. And because you do that, you will increase the amount of blue basic conjugate base. You're blue. Okay, that's for litmus. Now, there are many types of indicators. In the picture, those two are the most common ones. You have bromothymol blue, which turns blue at pH 7 if it's basic, and turns yellow at pH 7 if it's acidic. If phenolphthalein turns pink, magenta, purplish at pH of 9 if it's basic, and turns colorless at pH of 9 when it is acidic. Okay? And on this page, you see that there are many indicators. They all have their own pH that they change color at. The three most common ones that we use is methyl red, I'm going to highlight those, bromothymol blue, and phenolphthalein. You can see that methyl red changes from a red color to a yellow color when you reach a pH of 5. The bromothymol blue changes from yellow to blue at 7, and phenolphthalein changes from colorless to, well, it says red there, it should really say magenta, at a pH of 9. Which one you choose depends on the equivalence point of your acid-base neutralization. If we're talking about a strong acid, strong base neutralization, it changes color. Well, the equivalence point should have a pH of 7, so the indicator should change color near pH of 7. Near, not at. You don't have to be at pH of 7. pH of 5 and a pH of 9 within that range is okay. Because if you recall the shape of the titration curve, it looks like this. Okay, with 7 in the middle, pH of 9 really high, pH of 5. You can see that from 5 to 9, there's a jump. Okay, the volume barely changed. If you extrapolate, the volume stayed the same, but the pH drastically rose. So it doesn't really matter if you change color at 5, 6, 7, 8, or 9, because it's pretty much the same volume. So that's why phenolphthalein, an indicator that changes color at pH 9, is the most commonly used indicator. It doesn't have to be 7. It's good enough. You're not going to use methyl violet. Okay, if you decide to do a titration and you pick your favorite color, oh, I like violet, you add methyl violet, well, the color will change at a pH of like 0.7. That doesn't really tell you anything. Okay, you add some base, oh, look, the color changed. Well, congratulations, the pH is 1. Right? You didn't reach the equivalence point of 7, so that doesn't help. It has to be something between a pH of 5 and 9 that the indicator will change color, only then would it work. All right, so since indicators are weak acids in equilibrium with the conjugate base, they will have a Ka value. So consider this generic indicator of equilibrium. So the protonated version with the H in water, you get the conjugate base and H3O. Ka is therefore the product over the reactants, right? You exclude water. When you have more concentration of the acid, then it will be red. If you have less acid than base, it will be blue. And if they're equal, it should be between red and blue. It's a transition. You see both colors mixed together. So red plus blue, you mix to get purple. All right, so here's where your elementary school art class will come into play. you have to kind of know what colors existed between two other colors like blue and yellow, mixed green, that kind of stuff. So when you're exactly at the equivalence point or the end point for the indicator, you're in between the two colors. Right? And the color will begin to change when they're equal. And this happens very fast. All right? It's not like you're going to see that intermediate color for very long. It basically happens in a second. It went boom, and it drastically went from one color to the other. It's very drastic. Too bad I can't show you. When the acid is equal to the base, they will cancel in the Ka expression. You see what I mean? They cancel because they're equal. Only works if they're equal. All right, so Ka equals to hydronium at the pH that it changes color. If you take the negative log of both sides of this, you have negative log of Ka equals to negative log of hydronium. But wait, what is negative log of hydronium? That's the pH. Okay, and we define negative log of Ka as pKa. Right? There's pH, there's pOH, well, there's pKa as well. It's just the negative log of Ka. So the pKa equals to the pH if the pH is that special pH that it changes color at. So this proves that the pKa of an indicator is equivalent to the pH in which it changes color. That's how we define a pKa. If you see a table of indicators, you might see a pKa number attached to it. That simply means this indicator will change color at a certain pH. That's the pKa. Okay, so you have to choose a suitable indicator. The pH at the equivalence point of the titration must fall within the pH range of the color change. Otherwise, it's not going to work. Right, so does this make sense? What a pKa is and how that relates to pH? So you have many different types of indicators. They all have their unique pKa, the different pHs that they change color at. All right, and it depends on the titration. You choose the one that matches your equivalence point's pH. All right, so that would basically conclude this lesson. We learned about titration, we reviewed about titration. We talked about what an equivalence point is. We talked about what indicators are. We did some calculation regarding strong acid, strong base titration. We showed the titration curve. Okay, we calculated pHs. And we also talked about indicators on how they are weak acid and equilibrium with the conjugate base, and the color changes due to Le Chatelier's principle. The pKa of the of the indicator is equal to the pH in which it changes color. Do we have any questions?
I'm confused what pKa is.
Okay, pKa is basically an arbitrary value we defined to match the pH at which the color changes. It's another way of saying the pH at which the color changes. You see how that's cumbersome to say? You don't want to say the pH at which the color changes. Just say pKa. You see what I mean? It is derived when the acid is exactly equal to the base in the indicator.
Okay.
Okay, any other questions?
I have a question for the homework.
Right.
Yeah, weak acid and bases.
Weak acid and bases. Okay, hold on. So let me stop the stream then.